Eiffel combines the power of object-oriented programming with all the mechanisms that you can find in a functional programming language. The mechanism that unites the two paradigms, functional and object-oriented, is agents. And in this video, we're going to see how to work with Eiffel Agents. So Eiffel fundamentally is based on the notion of class, which is the core of object-oriented programming, and each class, of course, represents a set of possible objects. And objects are what our data structures contain. So at runtime, we have all these objects that contain references to other objects and other values. Sometimes, what we would like to put into these data structures are operations, but operations are not objects. So we are going to transform them into objects, and this is what agents are going to enable us to do. Let's take an example. That example is going to be a numerical example, but there's nothing deep about numerical analysis here. It's just high school mathematics. We want to compute the integral of a certain function. In this case, I'm taking the example of the cosine function between a certain lower bound A and an upper bound B. So this is how we would express it mathematically, and of course we cannot compute the exact integral, but we can approximate it for an arbitrary function f. So the trick is going to be able to compute this not just for cosine, but for an arbitrary function. So how do we compute an integral? Well, we approximate it. So this is the function f. It's not the cosine, of course. It's an arbitrary function. And of course, the integral is the area behind the curve, between the curve and the horizontal axis. So we approximate it by computing the sum of the areas of these small rectangles here. So in other words, we compute the sum of f of x times step for a whole set of values of x, which are all of the form a plus I times step for some integer I up to b. So at each step through the algorithm, we're going to have some x, which is a plus a certain number of times step. Then we are going to have step, we have f of x, and we compute the product of f of x and step, and then we sum this over this whole set of rectangles. We can write this in a very simple fashion in Eiffel for a given function f. So far we know the function, so there is no particular difficulty here. For example, the function could be cosine. So what do? We go from a to b, and at each stage through the loop we increment result. I'm assuming, of course, that result was initialized to 0. We increment it by this exact value of f of x times step, which is the area of this little pink rectangle here. Then we increase I and we move x to the next value, not by incrementing it by step, which would accumulate the numerical error, but by recomputing it from scratch as here. So this is the algorithm, and it's a standard numerical algorithm. It's very simple and there's nothing fundamentally new with it. But what we want to do is to be able to do this not just for a known function f, but for an arbitrary function, not just the cosine, but a function that we don't know. So we need a general mechanism that I'm going to call integral. It's a function integral, which is going to be in some class integrator. I'm not writing the class, but since this is object-oriented, of course, we want to have everything in classes, and we are going to have some integrator class with a function integral, and what we will pass to that function, and that's the important point here and the new point, is an agent. What's an agent? It's an object that represents a function. In this case, I'm passing to it an agent representing a cosine, but of course it could be any other function from reals to reals that we care to integrate. And so this is the way we're going to use this agent mechanism. You see that it's extremely simple. You can take any function in general, any routine, any operation, and pass it as an agent, define an agent around it, and for example, as we are doing here, pass it as an argument to a routine such as integral. So how do we write that function integral? Because of course what I've shown you here is the easy part. We build an agent, there's almost nothing to do, just take an existing routine and write agent in front of it, and then you get an object that represents that routine? Well, we had here the algorithm applied to a known function, and now we are going to make it applicable to an arbitrary function. So now f is no longer something that we know, it's an argument of the function integral, because integral should be able to work on an arbitrary function from reals to reals. So how do we declare this? How do we say that f is going to represent agents that themselves are associated with routines from reals to reals? Well, this is exactly the trick. We take this library class function, which represents in general agents representing functions, meaning routines that return a result, and then you can see that function has some generic parameters. The first one represents the argument and the second one represents the result. Or more precisely, the first one represents the type of the arguments and the second one represents the type of the result. Now we have a problem here because we want function, it's a library class, you can see it under Eiffel Studio, we want it to be completely general, so it should be applicable to any function such as cosine. Any function, but also a function that could have any kind of arguments. So we need to have a way to type in the sense of typing, in the sense of giving types to variables. We have to be able to type the class function, and for this we use tuples. What's a tuple? A tuple is simply a sequence of elements. So in general I can write tuple of ABC to denote sequences of 3 elements or more, the first of which is of type A, the second of which is of type B, and the third of which is of type C. So here we expect to integrate a function that takes just one argument, hence a tuple of just one element, real, and that function is going to return a real. So the second generic parameter here for function is real. So this means that we have a function that expects a real and returns a real, as is the case for cosine, for sine, for square root, all the usual functions of analysis. So that's the first thing that we do for integral. Of course, it also has arguments a and b, which are ordinary arguments representing the bounds of the interval. And then at some point, if you remember the previous algorithm, we did f of x. And so what we're going to do now is f dot item of x in brackets. If you're a little scared by the notation, just wait a minute, it's going to get simplified. But I want to give you first the full story, the full details. So what's f dot item of x? Obviously, it's going to represent this f of x in a mathematical notation. Well, here's how it works. If R is a routine, and we have a routine we have an agent based on R, agent R. Okay, for example, we could have had the argument, the assignment A receives agent R. Okay, so A is that agent. So it's an object that denotes R, possibly, as we're going to see, with some arguments already set. This is not the case here. And so in that case, using A, you can use call or item, depending on whether R was a procedure or a function. If R is a procedure, it means it doesn't return any result, so all we can do with it is to call it. If R is a function, its purpose is to return a result, and so in that case we can use item. So if I do a.call of x and y, the tuple xy, it's equivalent, if I knew what the routine R was, to directly calling R with the arguments x and y. And you see why we need the tuple here in principle, because call is a completely general mechanism. It's a library mechanism, so it must be applicable to any kind of routine whatsoever with any kinds of arguments. And so for typing purposes, for static typing purposes, we need to make sure it is well behaved for the Eiffel type system, meaning it's a tuple. And same thing for item. Using a.item is the same thing as in this case, calling R directly, and so we get a result that we could, for example, assign to some variable v. But of course, when we use the mechanisms on the left, the difference with the mechanisms on the right is that we only know A. A could be, for example, a formal argument of routine, so we don't know R. In different executions, A could be an agent representing different routines R. On the right-hand side, we know R, so we can call it directly. There's no need for agents. But on the left-hand side, we're just given an agent and told, call it if you like. And that's exactly what happens in our example with the integration. We have here item applied to a function f, and we don't know what f represents. It could be sine, it could be cosine, it could be square root, so we pass it a tuple. Now this is the full syntax, but in fact we can simplify it. There are two important simplifications. There's a general rule that when you have an argument to a routine which is a tuple, in most cases, whenever there's no ambiguity, which is almost always the case, there's almost never ambiguity, we can just drop the brackets. For both call and item, in fact, for any routine whatsoever. This is not specific, it's a general Eiffel syntax rule, so you can just say a.call of xy, a.item of xy, so it's the same thing, but it's nicer to read. And then the second simplification is that in a class, you can have one routine which has the parenthesis alias, meaning that you can call it directly with a parenthesis. And of course, in class function, which is the library class for function agents, and in class procedure, the other library class for agents, which represents routines, agents associated with routines representing procedures, call in the case of procedure and item in the case of function are declared with this parenthesis alias, meaning that instead of a.call of x and y, which was already an abbreviation from the version with brackets, you can write just a of x and y. And instead of a.item of x and y, you can write just a of x and y. So in our example, with initially f.item of x with item and with the brackets, we can simplify this and write this just as f of x. So you can see the elegance of the resulting code. In fact, this was the first code that I wrote. In the case we knew the function f of x times step, well, now we have exactly the same code, except that f is this argument of the routine. It represents an arbitrary function. There's one important other mechanisms that we need to see in connection with agents that gives you extra flexibility. It's the ability to have open arguments. Initially, our example was that we wanted to compute the integral from a to b of a certain function with one argument, for example, cosine or square root. And we use for that integral of agent cosine. I'm ignoring here the integrator object. Now, what if we now want to sum f3 of xu7 over that same interval, and f3 is just an arbitrary function. It has that name because it has 3 arguments. So we want to integrate it over x, of course, but we also want to pass 2 other arguments. So do you think we have to write a different integral function? Well, no, not with Eiffel Agents. What we can do is use open arguments. So what open arguments mean is arguments that are going to be specified at the time of each call and not at the time of the definition of the agent. So u and 7 are defined at the time of the definition of the agent. They are fixed at that time, but x is going to be provided each time we call f3, and the syntax for this is question mark. So when we earlier wrote agent cosine, it was really an abbreviation for agent cosine of question mark because the single argument is open. But there's an obvious rule that if all arguments are open, then you don't have to write parentheses, question mark, question mark, question mark. Say for 3 arguments, you can just ignore the argument list altogether, and it has the same semantics. This mechanism of open arguments gives us a lot of flexibility because we can use the same operations for many kinds of different routines. I've given you just one example, which is a numerical example, but Eiffel agents have many applications. In particular, if you look at the powerful graphical user interface library for Eiffel Vision, it uses agents a lot, and that's understandable because very often when you have a graphical application or a web application for that matter, what you want to do is that when the user does something, for example, clicks a certain button, the program will execute some operation from your application, but the library, the Eiffel Vision library, does not know about your application. So what you do is you pass a certain routine and say, whenever the user clicks this OK button, execute that particular routine. And of course, how do you pass that routine? You pass it as an agent. This is the general style used for user interaction in Eiffel Vision. Another important application of agents is iteration. Often you want to apply a certain operation to all the elements of a data structure, so you want to traverse the data structure, and for every element that you encounter, say, apply this operation, but of course you don't know the operation in advance. You only know it in specific cases, so you pass it as an agent. We've seen that numerical applications are an important application of agents, and in general, anything that you can do with a functional programming language, of which many exist around, you can do with Eiffel. You can use higher level functionals, that is to say functions that take functions and return functions that themselves can be also high level functionals. So you can do all that you would do in a functional programming language in Eiffel thanks to this agent mechanism, and there are many other applications of agents. So what we've seen is that this notion of agent, a core part of the Eiffel mechanisms, reconciles object-oriented and functional styles of programming. It makes it possible to encapsulate any operation in objects, and it's one of the great tools of Eiffel programming, complementing all the others that we are seeing in this series of Eiffel videos.